Given a 4 kilogram block that is pushed by a 36 newtons per centimeter spring that is initially compressed 6 centimeters, what total distance will the block slide given a coefficient of friction mu is equal to 0.50? This sounds really complicated, right? And definitely doing this with forces, probably impossible, to be honest. But we're going to approach this with energy. Now, something to recognize, there is friction here, so that's a non-conservative force. So I'm going to use that to help me recognize that maybe the tool I'd like to use is work is equal to a change in energy. And there's going to be work done by friction, so I'm going to already identify, you know what, this is going to have to do, something with friction here. It's going to be what that work is related to. But I'd like to think a little bit more about what I'm going to apply this to, because in that sense, like, what is my initial state going to be for this process? I mean, I've got this picture here, but I'm going to describe the initial state as the spring is compressed. Okay. Now, what should my final state be? One option that may be a bit of a pitfall, although it's still possible to do it, but you have to do something else, is to say that the final state is when the spring is no longer compressed. But I need to be a little bit more specific, because what's going to happen here is the spring is compressed, it pushes the block, friction is already happening the whole way because there's this coefficient of friction, but at some point the spring winds up being completely uncompressed, and then the block just lets go and keeps moving, right? And then at some point further down, it finally comes to a stop. So I think what my final state should be is that spot where the block comes to rest. So I'm just going to say block at rest represents the final state. And the reason why I think that that will work is because when I'm asked the question, what total distance will the block slide? This initial state to this final state represents that total displacement as a description. So if for that to be somewhere in this analysis, that's why I think I needed to choose those. Now, I'd like to think a little bit before I proceed about the system that I'd like to include here. The system is, of course, going to probably need to include the block. I think that's pretty straightforward. But I'm also going to include the spring in the system. I don't think I need gravity here because this is all happening on a level surface, so I don't need gravity. I'm not going to need to worry about any MGHs here, but definitely there's a spring energy. What about friction? Can I include that in the system some way? No. It's a non-conservative force. Has to be work. Okay? So how do we proceed from here? Well, we have that that work by friction. Maybe the way I could actually write this is I'm just going to say that's going to be force of friction times displacement. And this displacement D is actually going to be the thing I'm going to try to solve for, I think, right? Because it is the total displacement from initial to final. Now, what about possible energy forms here? Let me kind of write down what are some of the possibilities, maybe somewhat generically, based on the choice of system. There could be a change in kinetic energy. The block is, of course, sliding and stuff, so there could be kinetic energies there. But there's also this spring, so I think that means there could be a change in the spring potential energy, and I'm going to symbolize that with a delta U sub S. Okay, so everything's still a little bit general here. Based on the initial and final that I chose, though, when the spring is completely compressed, the block is starting at rest, and then it's let go, right? But that means initially the block has 0 speed, and the block also ends at rest, so finally it's also at 0 speed. So that means actually this change in kinetic energy is 0, so I can just knock it away. What about the change in spring potential energy? Well, initially, the spring compressed could be represented by a 1/2 k x squared, where I'm going to assume that k is given by this 36 newtons per centimeter, and x is given by the 6 centimeters. But in the interest of space, I'm not going to worry about the numbers just yet until I get a little bit further down. But in the final state, the spring is uncompressed, so that really means it's going from this to 0. So the overall change for that is actually a minus 1/2 kx squared, because it's final minus initial. So it's kind of like, in that sense, explicitly I could say 0 minus 1/2 kx squared for that. This one was already made as 0, so I don't know, maybe I could put 0 plus 0 minus. We'll simplify all that in another step. What can I do with this? What is the force of friction equal to here? I think a force-based analysis would show that it's equal to that coefficient of friction times the weight. And then I'll multiply that by d. And what do I base that on? Let me kind of go down to the corner right here. Right, this block, if it's sliding along, it definitely has a normal force pointing up. Right, it has a gravitational force pointing down, and it has a friction force. And since friction force is equal to coefficient of friction, this is sliding friction, kinetic friction, so we can just say it's equal to normal force. But based on the diagram, we know the normal force exactly counters the weight, so it's equal to that, and that means it's equal to just mu mg. Sorry, I had a button there. One issue, though, that I may be mistaken on here is, should this work be positive or negative? Recognize that the direction of the displacement of the block is to the right, but friction is to the left, right? So I didn't put that here, but the direction of the displacement is like that. So I actually should have had a minus sign in here all along. This is a negative work due to that. So let's make sure to include that. And that'll make sense because really at the end of the day, I've got minus mu mgd is equal to minus 1/2 kx squared. I can maybe knock away those minus signs, get rid of all the zeros, and just say therefore mu mgd is equal to 1/2 k x squared. And so recognizing that d is the question, right? And let's associate, like, right, we got some different values here. We got m is equal to 4 kilograms. I think k, the spring constant, that's really 3,600 newtons per meter, just to convert to SI base units. And in a similar vein, x can be stated as 0.06 meters. And of course, g is g, 9.81 meters per second squared. But the one other thing that I got from the problem statement is that the coefficient of friction is equal to 1/2 or 0.5. D is what we're solving for, so I'm just going to divide both sides by the mu mg there, and I'll just put the 2 down here with those things I divided by. And then this is something that is reasonably straightforward now to calculate, because I'm going to have the 3,600 newtons per meter, and then multiplied by 0.06 meters squared, divided by 2, multiplied by 0.5, multiplied by 4 kilograms, and then multiplied by 9.81 meters per second squared. Barely fit all that there. All right, so in the calculator, I'm going to do 3,600 times 0.06 squared, and then divided by the 2 times the 0.5 times 4 times 9.81, all that in the denominator. And my calculator spits out the number 0.330275, etc. But maybe I can just round that off to 0.33. I think it's going to be in meters, right? I mean, the units here are kind of complicated. I've kind of got a newtons down here, though. Would cancel that newton. One of these meters can cancel with that one, but that still leave 1 meter left over, so I think I can see it now. I could also state that if I wanted to as a total of 33 centimeters. And that's really the total distance from where it started with the spring compressed to where the block comes to rest.